Welcome to Roboy's Research Reviews, or the Project Arcute. This is a new initiative of Roboy where we bring you the state of the art research and try to explain it to you in 2 minutes. But before presenting a very interesting paper in robotics, let me introduce Roboy to you. Roboy is a humanoid robot that we are building to understand how the human body works. What makes Roboy really special and stand out from the other robots worldwide is that he has muscles and tendons instead of electrical engines in the joints. That results in many advantages as it comes to exploring the human-machine interaction. Roboy is built by a team of students and researchers, mostly from the Technical University of Munich, and it's an open source project. So if you're interested, check out our website roboy.org or the GitHub account github.com/roboy. We are all aware that parrots are good mimics of humans, but what if robots could also mimic and learn from humans? The amazing paper we have on our hands today is DeepMimic, example-guided deep reinforcement learning of physics-based character skills. They talk about how reinforcement learning trained with motion clips provides a promising approach for motion synthesis. An agent learns to perform various skills through trial and error. The central contribution of this paper is a framework for physics-based character animation that combines goal-oriented reinforcement learning with data in the form of motion capture clips. Up until now, most of the state-of-the-art kinematics methods are manually designed controllers that are trained with deep reinforcement learning. In this work, the authors present a method to bypass this problem by directly rewarding the controller for produced motions that resemble reference motions, while also involving task objectives. The input of the system is the character model. The synthesized controller enables the character model to imitate the reference motions. Each reference motion is represented as a sequence of target poses. A control policy maps the state of the character and the task-specific goal to an action. This policy is used to compute torques to be applied to each of the character's joints. The policies are modeled using neural networks and trained using a proximal policy optimization algorithm. The policy reduces the desired motion in a physically simulated environment from the motion clip. The policy decides which action to take at each time step in order to realize the desired trajectory. The policies are trained with a proximal policy optimization algorithm in multiple mini batches. Initial states distribution initializes the character to the starting state of the motion and allows it to proceed towards the end of the motion over the course of an episode. With this design, the policy must learn the motion in a sequential manner. Early termination terminates either after a fixed period of time or when certain termination conditions have been triggered. For example, if a robot falls down, it terminates the action. So why stop with a single action when you could multiple things together? With multi-skilled integration, they give the ability to compose and sequence multiple clips. The exciting characters in this paper are a 3D humanoid, an Atlas robot model, and wait for it, a T-Rex and a dragon. Well, why not? The characters are trained to do a fancy lot of interesting tasks like target heading, striking, throwing, and traversing a terrain. The final result of the system is a policy that enables a simulated character to imitate the behavior from the reference motion while also fulfilling the specific task objectives. The resulting policies are highly robust and produce natural motions that are nearly indistinguishable from the original motion capture. Their framework is also able to retarget skills to a variety of characters, environments, tasks, and multiple policies. The performance of all the characters performing the various tasks have been shown in these impressive simulations. While we have just scratched the content of this paper, we encourage you all to go read this fascinating paper. I'm sure you've heard of the NIPS challenge. We at Roboy are really passionate about how prosthetics could change the way how we deal with disabilities. So for the winners of the NIPS challenge 2018, we give the opportunity to work with our Roboy here in Munich. So if this sounds exciting, you should definitely write to us. So what do you think about reinforcement learning? Let us know in the comments below. And stay tuned in for more cool papers.